So, yes, this is a work that we have done. I'm working at the University of Bristol as a postdoctoral research associate in Sphere, which is a project that aims at monitoring human behavior in living environments for the home healthcare. And the work is aimed at person identification using deep compact networks, using controlled augmentation and network compression. So by controlled augmentation, I refer to obtaining representative synthesis from large training sets, and for network compression, I refer to producing small and deployable networks for identification that can be suitable in reasonable and priced devices. So the storyline of the presentation is a motivation in the field of person identification, which is actually a field that the domain is very wide depending on whether we consider outdoor or indoor scenarios. Then the proposed compact pipeline that has been recently submitted for BMVA, and I'm focusing on an indoor data set that was published before for indoor living environments, and then some experimental results and conclusions with some feature considerations. So for the person identification research field is interesting because it has many potential applications of impact, and I have focused on two of them. One is the surveillance, where usually happen in outdoor spaces or very big places where we want to recognize many identities from a large set of training images. And the other application, which is the one that I'm focusing for in this talk, is the indoor living environments, where we usually have much fewer number of identities to be recognized continuously during all the time. So the identification is more focused on that. But it's also considered could be considered as a person identification problem. So the challenges from the computer vision side are that we can have unobservable intervals from the multiple cameras that we can have in the scenario. So we could have some missing data. We could be missing some relevant data from that. We also have the problem of varying appearance. So the person that is changing the clothes at different stages of the session, illumination changes, occlusions, also low resolution images, the non-frontal shots problem that could make the facial geometrics not applicable, and some problems which refer to the limited amount of training data that could make difficult the identification of people in the long term. In the long-term fashion. And other practical challenges that refer to the vast of training data that are required to train these deep neural networks, as well as the inference to perform inference that requires usually high computational resources. So the solution that we proposed for that is a compact identification pipeline, which considers a training set data captured from sensor cameras and a person detector, which stores the bounding box of different images. And then in the middle, we have the control data augmentation module that will synthesize new images, and at the last stage, it will feed the deployment network in order to output the vector of identity scores. So at the core module, we have two submodules, which are the facial prefiltering network that will filter out the content from the training set, depending on the presence of a face from the original images. And then, depending on the training strategy, we will input these images into a generative process that will synthesize new images, and in combination with the original images will be used to feed another last network for inference, which is a deep compressed identity network that will basically do a discriminative training from the new set of images. And at the last stages, we have an optimization process that will compact the network to make it deployable in small devices. So, therefore, the key subnetworks are the prefiltering network, prefiltering facial network, which is based on the open pose phase detector, and it basically filters out content, cluttered content from the input images in order to focus the synthesis to those images that contain unique representations specifically for every individual. Then the image synthesis is done using deep convolutional generative adversarial networks that will produce this novel imagery data. And the augmentation can be on two purposes. And so we can obtain generic generators from the whole training set, or we can build generators for every class individually. And then the third network is the compact inference network, which is a compressed context network that consists of learning grouped convolutions in the dense layers, and then discard those unused weights in the optimization stage at the last stages of the network. So you can produce a fast inference for identification. So about the data set where we performed experiments is a long-term identity monitoring data set that was acquired 2-3 years before. It consists of about 200,000 images, where we have 6 person identities, and there is one additional identity that is obtained, that are images obtained from a person detector, which are not belonging to any particular person, or it can be background, it can be some noise, some guests, people that are not residents of the home. So this is a challenging environment in the sense that we can have multiple people, multiple cameras, low resolution images, because it is changing the position. We have images that follows the temporal covariance, and we split the training, the validation strategy from for the evaluation protocol of this method is a leave one out validation that splits the session, it splits the whole training set, the whole data set into 13 sessions. And another challenging thing is that in a single session we can have people that change their clothes at different instances of the session. So these are some of the examples of using our methodology for synthesizing a new set of images. So these are the images generated by the networks, either using the semantic controller as a phase filtering. So in this big case, we have the images that are generated using a facial per-filtering network, which we could say that looks like person images, more or less, with respect to the first case on the left, that we are not using a semantic controller, we are not using facial per-filtering, where we have more repeated noise textures, usually from the background, and cluttered content that is mainly produced by the distractor content from the class that is not a person. And these are some of the results. So we again, in this case, we are generating images specifically for every identity, and in this case, we found that this is working best in the state of the art when we are trying to identify only person from the mean average precision metric. And there is another case that is outperforming the state of the art with respect to the previous works, that is using augmentation from the whole content, so for all the classes, including the non-identity class. But it's important to notice that the amount of synthesis has to be balanced to the amount of original training set. In this case, we are using the 50%, around the 50% of synthesis in combination with the original data. And we report the results in terms of precision at the top 1 classes, which is actually the classification accuracy. And another case that is of interest is the, for comparison, is the case where we are not using augmentation. So we are directly training our R, which is the compressed deep network, using the semantic controller, but without producing any augmentation. And in this case, it's interesting to know that we are losing performance down to 10%, mainly because of the distractor content. So we analyzed this case in more deep because we saw that there is a training restriction in here when we filter the images, because we are losing around the 40% of critical identity relevant information from the individuals. And if we filter the images from the test as well, then we can see that in the test sets, we can see that the results then gets better. Although these of course are not comparable to the state of the art, was just to show the performance of the pre-filtering method. So some other qualitative results. Sorry for the video because it's flipping the images between 2 different cameras that are happening at the same timestamp. But the main idea is to see that for some challenging positions, like the lying position, there is a drop of performance when we are not applying a phase of filtering network before. And this problem becomes alleviated when we apply the phase detector as a pre-filtering stage. However, there has to be a balance between the use of the pre-filtering network and the augmentation if we want to generalize, also if we want to recognize the distractor content. So in the plot top, we can see that in red, the class that is difficult to be recognized mostly is the distractor content in red, and the other identities which refer to person are better classified. And in the other figures on the left, we can see some correct detections and failure cases. Correct detections in cases that we have changes in clothes, so people are changing their clothes in the different parts of the same session. So as the conclusion, the content re-identification approach is presented that uses control data augmentation and compression to perform fast inference. And we have seen that constraining the generator networks using pre-phase filtering network outperform the long-term monitoring in the data set from the state of the art. And for future considerations, it's interesting to explore other semantic controllers that have to be beyond the face. So we can use other controllers like the pose, or to be able to build more generic networks as part of the discriminative stage of these networks. And also it will be interesting to use also learn these generators from other person-like representations, so they are not only limited to the RGB data, but it would be also very interesting to see what happens if we synthesize images from the silhouettes or from the depth data, especially for the privacy reasons that happens in the living environment. And yeah, so yeah, that's it. Thank you.
Enjoyed the talk. So the punchline about augmentation is that it helps all the time.
Yeah, the point is using augmentation, the networks becomes more generic to identify identities when they are combined with the original data.
And can you say a little bit about what care needs to be taken when you do augmentation?
Yeah, when you do augmentation, there is a case, especially here, when it's interesting to focus the generation in a specific content. So we can do the generation focusing on particular identities, particular persons. So we know the class from which we are generating the data, and in an ideal setting.
So give specific example.
In an ideal setting, we would have all the images that are synthesized amongst all the classes. So the same number of synthesis and the original with respect to the original data. But in our case, we don't have we found that learning the generators from the whole content was working better, but it worth to explore this case by synthesizing a specific number of images for every class.
Sanitization is not augmentation.
Yeah, we are considering here synthesizing as an data augmentation approach from the dissidents.
Thank you.
So I might have missed that, but can you talk a little bit more about how much you lose in your precision or whatever your metrics are when you do the network compression, and how much you gain with that in terms of performance? Did you look at that?
In terms of performance, with respect to the state of the art, if we directly use the network, so we use directly the original image fit to the deep compressed network, it is able to generalize better to the specific changes in appearance with respect to the state of the art. But in the state of the art, the results are only reported for the classification accuracy on all the classes. So we are proposing additional metrics where we focus the identification only for people, which is more interesting in the case of living environments, and also some additional metrics for the lab. And the interesting point is that the inference is faster with respect other networks that uses also dense convolutional layers, but uses like 600 million more operations to perform inference into a single image. That's the point. The results get better, but the inference cost is also increased a lot.
Okay, I also have a very, very quick question, I think. How applicable this would be in an environment where the people change all the time. Like you have a person coming there for 3 days and then leaving.
Yeah, that's a very good point. Because in case that we know the residents of home, we have few identities to be recognized, and we don't really care about the other identities. So this is why it's interesting to see both cases. Like the case where we add this additional case. So in case that we have guests, we just are considering as identities that we don't care. So it should be trained in, as far as we have until the moment. It should be trained depending on for every in the project that we are working. For every house, we should train the network. But in the work that we have published recently, we are trying to use synthesis from other data sets in order to see if additional data that comes from other different environments could be used in combination with a specific environment.